All right, so let's do a Mathcad example to see how this all fits together. Right? So we're going to have this, and we're going to put that into what we're seeing here. So we're going to do a step-by-step process here, looking at this truss. All right, so basically just triangle, equilateral, 100 inches for one element, 100 pounds being applied horizontally here at the top. The modulus is 1 times 10 to the 6th psi. Got an area here, 0.1 inches squared. E times A is, we're going to see this commonly, so we're already going to multiply that out, 100,000 pounds, and again, length of one member is 100 inches. So we're going to be finding the displacements of each node, the support reactions that are pinned in our roller joint here, and we'll also look at the stresses in each element, solve for that. All right, so let's get to it here. All right, so just following that solution path that we have for finding an element. First is the pre-processing phase. We need to determine what the nodes in our elements are. We need to declare what they are up front. So this is what we're going to do. We're going to say we got node 1 here in the bottom left, node 2 on the right, node 3 at the top, and then element 1, 2, and 3. And again, we have to specify very carefully how these are set up. So here's a table to show you that. Element 1 is made up of node 1 and node 2. And referring back to what we talked about previously when we talked about node I and node J, for element 1, node I is 1 right here, and node J is 2. So when we look at theta, we're measuring up from the horizontal. How does node J move up from the horizontal? It doesn't in this case, so our angle is 0. I forgot to put the degree sign there. Kind of try to fit in there real quick. And so then for element 2, node I is node 2, and node J is 3. And you can see if this member kind of started out like this, and then it worked up, and we measure the angle like this, we would get an angle of 120 degrees, because this interior angle here is 60. So the outer one here is 120. You could also do it differently. You could also have said element 2 is node I is 3, and node J is 2. And again, if you measure from horizontal, you could either measure this way and go around, or you can measure this way. All right. As long as you're consistent and you get these things right, you're okay. I would just focus on horizontal here. 2 and 3 should work out just fine. All right. Let's look at element 3. So element 3 is right here. Node I is 1. Node J is 3. So just measuring up from horizontal, and we're going to get 60 degrees. That's where the 60 comes from. All right. So we got our nodes defined, we got our elements defined, we got our angles defined. We're in a good place. All right, so step 2, we're going to assume a solution that approximates behavior of an element. All right, so we kind of already did this. We said, okay, our equivalent stiffness is going to be our AE over L. And AE we already defined 100,000 pounds divided by the length, 100 inches. So our K, or stiffness value, is 1,000 pounds per inch. All right, so let's do that. Let's go see what we can do that in Mathcad. All right, so here's your Mathcad file. Oh, by the way, here I'm running Mathcad Express, so I do not have a license on this, what I'm running right now, so you should be good if you just want to download the free version of Mathcad. Sorry for the ads on the side. I think with Express, I can't get rid of that. All right, so here we go. We got the modulus, 1 times 10 to the 6th psi. We got the area 0.1 inches squared in the length at 100 inches. And by the way, if you haven't figured this out yet, I'll just show you how you can plug that in. If you, let's say M, and then M colon to define the value, say 90. And then if you want to put in the dimensions, you can just type in what those dimensions are, so 90 inches like that. And you should turn blue to indicate that it's been a dimension. So I just wanted to highlight that when you get a chance to do that on your own. All right, we got our diagram over here to see what's going on. So scroll down here, and we've got K is our stiffness matrix that we showed from before, the development of from the forces and the stiffnesses being applied to our single element. And I'm just going to click on that and hit equals to see what those values are. And everything else is in English units on this, so let's be consistent with that. That's what the note's here for. You'll need to change the units to pound force inches. So let's do that. We're just going to backspace out the kilogram inches and just type in pound force divided by inches. Enter. Right, you can see that comes out nice, much more clean values for us there. All right, so that looks good. So let's go back to the presentation here. All right, so we're going to develop equations for our elements. So we need the stiffness value, the global stiffness matrix. So that's our, here's our K value out front, multiplied by our cosines that have been set up here. So again, this stiffness matrix that we made over here in Mathcad, to be clear, local coordinate, right here, local coordinates, local form. I'm going to go back to the presentation. This is the local coordinates, but it's in the global form, where we're using the capital K. Right? We're in the local form because we're still got an E here. All right, so let's look at that. So here's our development of our global coordinates, but local form of our stiffness matrix. All right, so for element 1, we know the angle is 0 degrees. So we plug in 0 degrees up top, and we come up with our global coordinate form is what you see there. And we're going to do the same thing for element 2, put in 120 degrees. All right, again, these are all back from the table, back in step 1 when we define nodes and elements. We get the values there. And for element 3, 60 degrees, we get the values there. Okay. So I showed the corresponding nodal displacements because this is element 2 is made up of nodes 2 and 3. And element 3 is made up of nodes 1 and 3. All right, so we're going to head and do that, see how we do this. All right, so we're going to scroll on down here. So the transformation matrix, I already put this in. So that's for a truss. Now this is, the overall transformation matrix. So we're going to go down here to element 1, and we're going to put in the angle. So you can see it's radians to start with is the default. So we want to get our angle from degrees to radians. So for element 1, it's 0 degrees. And just hit enter there. So it's 0 radians. The transformation matrix, to make it easier on ourselves, I did this in terms of A. So A being the angle. And so the angle is defined here. So it's 0 at this point. So I'm going to type in, use the transformation matrix up above. That's a function of A. So look here for A, and I'll look here for the transformation matrix. I hit equals, and I get all my 1s. Right. So I'll slide down here. And now I want the global stiffness matrix, because again, up here is the local stiffness. Down here is the global stiffness. I'm trying to get the global coordinates. So we're going to pass through this one. We got T1, and just follow this form right here, or from the presentation. So T1 times K, which was defined above, times T1. And now you got to make sure you get the inverse. So caret or shift 6. -1, and we'll hit equals on that. All right, again, watch the units there. So we want to change this, swap this out for pound force per inch. All right, so that's what you should get there for stiffness for K1. Scrolling on down, expand this section. For element 2, we have the angle of 120 degrees. So plug in 120. Again, we get that to radians. Transformation matrix 2. Now A, because the way Mathcad works is whenever you redefine something that's already been defined before, this one takes over. So A now, because I've defined it as 0.02, it overrules the angle I defined above for element 1. So I'm going to put in the transformation matrix as a function of A. Right, so we get those values, and now I want to get the global coordinate form. So I'm going to put in T2 times my local stiffness times T2 to the inverse -1 equals. All right, again in kilograms per second, let's change that to pound force per inch. And we get that form. And scrolling down for element 3, we'll plug in our 60 degrees equals T as a function of A equals and T3 times K times T3 inverse equals, and change the units to pound force inches. All right, so that's what you should have there.